Tsao-Hsien Chen from University of Minnesota, Chen City, to talk about real groups, symmetric varieties, and Langlands duality. Welcome.
Okay, thank you for the introduction. So today I will talk about real group symmetric variety and the Langlands duality. So the plan is first, I will first discuss a remarkable phenomenon in this theory, which I call real and symmetric correspondence. So it goes back to Cardan's work on classification of real groups. And then I'll mention several kind of famous examples. And then I will talk about a new instance and new examples of this real and symmetric correspondence in the setting of Langlands duality and talk about applications. So first, real symmetric correspondence. So let G be a kinetic complex reductive groups. And a basic question in this theory is about classification of real form of this complex reductive group. So namely, we try to classify anti-holomorphic involutions on this group. So we have where it's identity, but it's not algebraic, it's anti-holomorphic. If put back, if a holomorphic function, the pullback will be anti-holomorphic. And then every time you have this, then you can take the fixed point, which is denoted by GR, and this is the real form of this complex reductive group. And the basic question is how to classify all of these. And so there's a similar question at the level of Lie algebra. So you just consider anti-conjugate linear Lie algebra involutions and try to classify all of them. And this is a question kind of slightly more difficult than the case of complex group because you're dealing with non-algebraic or anti-holomorphic things. And at the level of Lie algebra, it's a conjugate linear. It's a linear algebra over the real numbers. So it's more complicated in the complex case. But nonetheless, Cartan solved these questions and gave a very nice answer of these. But what is remarkable about Cardan's solution is that the way he solved this is as follows. So instead of working in this setting, he realized that this question is equivalent to another similar question, but instead of consider anti-holomorphic involution, he considered algebraic one. So G now is algebraic, or if like holomorphic, and involutions. And and try to classify all algebraic involutions. So this is equivalent to so-called classification of symmetric spaces or symmetric varieties. So here you can consider K to be the G theta, the fixed point, and X to be K mod G. So usually this is called a symmetric subgroup, and this is called a symmetric variety. So he realized that classification of real form is the same as classification of a symmetric variety. And turns out, and he solved the question here. And here is somehow simply because this is in algebraic setting. At the level of Lie algebra, it's just classify C linear involution on Lie algebra. Whereas now become the question in linear algebra over the complex. So it's simpler. And also here has a very nice feature that actually this question here is pure algebraic. It makes sense for any algebraic group over any algebraic closed field, say characteristic is bigger than 2. So it's very nice. And I will call this as an instance of a symmetric correspondence. So it's a phenomenon that In this theory, so somehow many representation theory about real groups, or Lie theory about real groups, has which is usually for real analytic of real analytic nature, has equivalent formulations in terms of the corresponding symmetric space or symmetric subgroup, which is purely algebraic. And every time you have such correspondence, you can create a game that move one question to the other side and vice versa, and bring two on one side to the other side. And so this is a very powerful thing. And turns out there are many such correspondence in this theory. This is basically the most important one and most basic one. And let me list other few kind of famous examples. So I will go to chart. Maybe here, real and align symmetric. So we have this GR, lissification real form. Turns out is the same as lissification of a symmetric variety. So this is due to Kaptan. And next famous example is about representation of real groups. So we consider GR representations. So this is really by definition, analytic theory. You have to use the functional analysis and the differential equations. And then turns out there's a pure algebraic equivalence theory, so-called the GK module. So G is the Lie algebra of the complex group, and this is due to Harshchandra. Harshchandra realized that there's a equivalent between real group representation, which is a real analytic, and the algebraic theory, so which is called the GK module, is purely algebraic. You just consider basically modules for the Lie algebra equipped with a compatible action of the symmetric subgroup. And this correspondence plays a very important role in the study of real representation and the representation of the Lie algebra. Okay, and well, for example, in this case, let me mention one application of this correspondence. So on the algebraic side, basically by Shor's lemma, you can talk about so-called central characters of a reducible representation of the Lie-algebra. And Harshchandra give a description of the center of the universal enveloping algebra. Hence, he can give parameterize what is central character, and this central character plays an important role in classification of real group representation. So these are the two fundamental examples of a real and symmetric correspondence. And let me mention another one, which is somehow close related to the thing I'm going to talk about. So it's due to Matsuki. He considered so-called the GR orbits on flat manifold. So Gma B is a flat manifold, and you can consider the whole group X on this, in particular, is a real form X on this. You consider the real orbits. And on the other hand, you can consider the K orbits on Gma B. Those orbits are very different because these are real analytic manifold. Here is the algebraic manifold. But turns out there's a bijection. So between these, usually called the Matsuki duality. Matsuki. Yes. Yes. So, and this is also very fundamental result in Lie theory. And actually, there's an upgrade of this due to Markovich, Usawa, and Vilonen, where he can actually upgrade this to an equivalence category. You can consider category of GR equivalent complex on flat manifold and the category of K equivalent complex on flat manifold. And turns out there's a non-trivial equivalence between these two. This is a more kind of geometric flavor of this real and symmetric correspondence. And again, once people realize that there are such things, and there are many consequences. Okay, so there are many few. There are other kind of famous examples related to neopolitan orbits, but now those three are the very classical ones. And so for today, I want to talk about a new kind of instance of this real and symmetric correspondence. So where on the symmetric side, I want to talk about, so we consider the loop space of X. And you try to understand somehow the R group, the LG orbits on this loop space. And so here I will relative Satake. And or more generally, you consider similar to that the whole category of L plus G R group equivalent shapes on this space. And on the real side is of the correspondence is I will call real Langlands for P1. P1 is the projected line. So basically, you try to understand, consider the bundle, the real GR bundle on the real projected line. So I will make this, I will recall the definition. And then the new instance I want to discuss is such correspondence, relate so-called the relative Satake or relative Langlands and the real Langlands for P1. If I have time, so I can also mention some kind of new development about so-called the twisted relative Satake. So where you consider R to X on so-called twisted symmetric variety. I'll recall the definition if I have time. And then here, you can consider it corresponds to real Langlands for not this P1, but for so-called twister P1. So usually we notify this. So you have a bound in R. So basically, the complex P1 has two real forms. The real P1 which has a real point, and this another real form has no real point. Usually, the real form goes like this. Turns out there's kind of a twisty version. Okay. So now, so before I talk about this, let me explain what happened in the case of complex. So the complex, let me just say, the complex Satake and the complex, I say complex line. So the main player here is so-called Frank-Grassmannian. So you have a GR, which is LG not L plus G. So LG is the loop group, formal loop group, and the L plus G is usually called R group. And then this quotient is usually called a Frank-Grassmannian, which is in the case of GLN, it basically classify all lattice inside C bracket E to the n. In the case of GLN, and this is a very kind of main geometric aspect in Langlands and geometry representation theory. And then you can consider L plus G, the R2 orbits on the Grassmannian. And more generally, you can consider they're very nice. Basically, by quantum decomposition, there's a very nice combinatorial description about R group orbits on a Frank-Grassmannian, and also from here you can consider somehow the shift Grassmannian, which is the L plus G equivalent. Usually, this is called Satake maybe here, the complex Satake category. The reason this category is important in the Langlands business, because if you consider the category of perverse shifts on this side, so you can consider perverse shifts on Grassmannian, which is L plus G equivalent, then there's a fundamental result for the geometric Satake. So this here, the G check is the so-called complex U group. And this is it's called a famous geometric Satake. And this is the basic result in Langlands duality. Just like the case of classical Langlands, the classical Satake is somehow the basic result in classical Langlands. This geometric Satake is the basic result in geometric in Langlands duality. And and turns out in this case, this complex Satake is related to complex Langlands on P1, and this is in some sense is a complex group version of this real and symmetric duality. So this result is due to Vincent Laforgue and published result for Roman Berezkovnikov. So namely, you consider bundles on P1. So this is the stack or moduli stack for G bundles on P1. This is a nice algebraic stack. And then the basic result, the theorem due to Vincent Laforgue and Roman Berezkovnikov. Shows that actually this complex Satake category is equivalent to shifts on moduli stack of G bundles on P1. So they realize that there's a equivalence really complex Satake and shifts both. And the shifts on moduli stack of G bundles on P1. Yes. No, this is the kind of real form of this thing. So I will give a definition of what is real bundles. Yes, yes. Yes. You talk about the case when you have when the GI is a complex group. Yes, I will talk about this very much. Any other questions? So and turns out this this correspondence is actually quite explicit. So let me explain. Okay. No. This is weird. All right. Okay. Okay. This side. Okay, maybe then. I think it's a little bit hard too. Yeah, the proof turns out this equivalence is given by a correspondence. So it's quite explicit. So namely, so you have a R, and then turns out you can consider just Grassmannian only model by G, which is somehow the constant loop. And then you can consider inverse. So this is a group where the polynomial group with variable T inverse. And then it's known that this is the same as bundles one. So this is usually called uniformization. Then, so you have this correspondence related Grassmannian and the bundles. And this equivalence is just given by you pull back and push forward. Just pull, push. And this is equivalent follows from the fact that it's an application of so-called Braden hyperbolic localization. There's nice GN action, the loop rotation, Grassmannian somehow realized related L plus GR orbits on Grassmannian and the opposite group orbits on. So it's very explicit. And an application of this, so you see, if you know this, which the proof is not very difficult, but then you realize that if you want to prove, give a whole description of this Satake category, this question now becomes the same as give a description of bundles on P1. And so if you can give a description here, actually you prove basically geometric Langlands in the case of P1. And if you can prove this, then vice this, you also prove geometric you prove so-called derived Satake for this. And this is actually how Vincent Lafort proved the geometric Langlands for this case. He just realized this, and then this turns out is already understood by the work of Roman and Finkelberg. They give a proof of derived Satake. No. So let me, so now I write corollary, well, but actually it's also Lafort. And Roman Pavnikov and Finkelberg. And they prove the following. They give a spectral description of the left hand side. So let me just write as I call to the dual group, more G hat, but with some ready shift, and then the log one. So basically, oh yeah, there's no. This side has no duality, and applications of Langlands is this. So basically, this is to this vertical one is due to Roman and Finkelberg, Roman and Finkelberg. They give a spectral description in the sense that they give a description in terms of Langlands global data, and then combine those two, you give a description of this the right hand side, and it turns out this easy somehow just duality exercise show that this can be interpreted as just local system on P1, and this is how one proved Mitchell Langlands for P1. And this is a very nice examples of real and symmetric correspondence, but in the case of complex group. Okay, so now what happens in the case of real groups or symmetric variety? So I will consider again, so the loop space is a formal loop space of X, and then R group acts on this, and then you can consider the category of a GI Givenchy on this space. I call this relative Satake category. There are many reasons why this is kind of interesting. One reason, actually, if you, okay, I will talk about it. In the case of so-called group case, this is exactly the complex Satake case. And there are other reasons from so-called relative Langlands program. Turns out, in the case, if you consider, instead of complex coefficient, consider finite field coefficients, then this is a basic argument in harmonic analysis on loop of into symmetric variety. Okay. And then, so this will replace the Satake, right? And on the bundle side, I consider real bundle. So we have, so P1 has involutions given by, so be the complex conjugation, sending Z to Z bar, be the complex conjugations. So it's a real form, and whose real point is P1 theta is the real P1, real projected line. And this involution, together with the involution on the real group, defines the involutions. So you have P1 and G. And there's an involution on this coming from the P1. So to define the involution on this moduli space, you need two involutions. One is on the base, on the curve, another is on the group. These two give you an involution on the whole space, and then you can consider basically it's a real form. So which is the basically like. So this is a real form of this. So this is a real analytic stack. And so the theorem we talk about, which is an analog of those results in this set, it can be thought as a real symmetric correspondence in the setting of Langlands. So there's equivalence between, then you can consider the relative Satake category. And turns out this is equivalent to G's on real bundle. And so somehow here, in something is purely algebraic, everything is algebraic. But here is, because we consider real form, here is a real analytic. But nonetheless, there's an equivalence like this. I will say more about this equivalence when we talk about application to Langlands duality. But so far, it's about this part, which is real and symmetric correspondence. And that's the analog in the real and symmetric setting. And turns out the proof is very similar to the complex case. The equivalence is given by very explicit correspondence. So basically, for now, let me save some time. Let's assume K is connected. Otherwise, I have to talk about component, which is equivalent to GR is connected. And then in this case, there's a correspondence like this. You have these quotients. X is a symmetric variety. So again, the basic set graph is you have real groups. and you have for X the corresponding symmetric variety under Cartan bijections. And then the correspondence given by this, so it turns out this is the same as you can change perspective. So you have a loop of K marked first minus. And then on the other hand, there's a similar uniformization for real bundle. Turns out there's a polynomial GR marked first minus. So where this the polynomial GR is those map from the C cross to complex group, sending the S1 to the R. You consider those polynomial map or algebraic map from C cross to G. When you restrict to S1, those complex number with no 1, it maps to the real form. So this is called a polynomial loop group of the real form. And this is clearly a subgroup of LG. And then it acts on this. And turns out this is the same as the thing we are interested in. 1R. So this is kind of a real uniformization. And then turns out you have a polynomial K, KR. So where KR is the intersection of G intercept GR. Then there's a correspondence like this, P and Q. And then this equivalence is again given by P up to 3. This is the proof for the construction of the equivalence. But then to show that this is the equivalence, you need another ingredient. Is that you need a construction of certain Morse flow, which we call the Matsuki Morse flow on the Grassmannian, which give you a bijection between somehow LK orbits GR and L polynomial GR orbits on GR. So in the case of complex group, this flow is coming from the derivative of this loop rotation GM action. But in the real setting, there's no such things. You need to construct some kind of Morse flow on the Grassmannian relating this orbit, the loop LK orbits, loop group of K, acting on this orbit, and this polynomial loop group orbits on GR. Once you have this, then the similar so-called Braden hyperbolic localization implies this is actually an equivalence. So this is the real and symmetric correspondence in the Langlands setting I want to talk about, relating somehow the relative Satake and the real P1, real Langlands on real P1. And now let me explain some applications of this. So I will talk about two. So the first application is somehow from real to symmetric. I want to consider some question, and turns out it's easier here. And then vice this, I get a solution on the symmetric side. And the second example is from symmetric to real. So the first application is about explicit description of so-called relative Langlands dual groups. So application So the first equation I will write real is symmetric. So on the real side, I consider the following. So as derived to x, is this equivalence compatible with some kind of monoidal structure? Turns out it's not. But turns out there's a variant of this which is compatible with many structures. For example, this equivalence is not exact in the sense that turns out they are both have natural T structure, but this one is not exact. But turns out you can correct it using the following result. So let's consider so-called real Van Grassmannian. Then you should consider just formal loop with R coefficient into your real form. And this quotient is this called the real Van Grassmannian. And then let me write this R plus. And the real R groups acts on this. And then similarly, this is a real algebraic variety, but actually the invariety, but defined over the real, and has this real group acting on this. Then similarly, you can consider the categorical shifts, this. So I will call this real Satake category. So it's just like the complex Satake, but you just replace your complex group by real groups. You can still consider real formal series into this group. And this is a very nice space, and this action is also very nice. They are very nice decision about OB and OB closure. Just looks like the case of complex. And the point is that, so we have the following theorem, and that the so-called the real Higg actions at the real points 0 in T1 R defines an equivalence between the bundles and shifts on real bundles and the real Satake category. So basically, if you're familiar with Langlands, this space has so-called Higg modifications. And in the case of real bundle, you have a real point, you can talk about real Higg modifications. And turns out then this defines the action of this real Satake thing. And turns out this is equivalence such that, and what is happening is that if you compose the real and symmetric with this Higg action, you get an equivalent with a remarkable property. The composition equivalence from the relative Satake or so it turns out this one is T exact with respect to perversity structure and compatible with fusion product. Fusion and the so-called the complex Higg actions. So it turns out if you compose those two, you get the equivalence which compatible basically all the structures. So here both sides have natural perversity structure, and this is T exact. And this has, just like complex, has a fusion convolution. Turns out they are the same. And here you have a fusion product, and this composite equivalent also compatible with fusion. And they also have a complex Higg action, and turns out this is also compatible. And now, and as applications, we get the following things. But at this point, okay, we get the equivalent, but we have no idea what is this and this. They're both still very complicated. But one nice thing about this is that turns out, so David Nadler's thesis is about this. He spent a lot of time on this, and he put some very nice result here. And now we somehow get something for free on this side. So let me just write what is the thing I want to conclude. So you have this real and symmetric kind of twist, like this composed one. And it will make perverse shifts on these. Two perverse shifts. On this side. So it turns out to define this requires some work. And on this side, it's just based on under my assumptions, all the orbits has even real dimensions. So there's a natural perverse function. And turns out you make perverse shift to perverse shift. But still, turns out this is still very complicated category. And the work of Gascoigne and Nadler, they single out a subcategory here, which I call principal block 0. Basically, they only consider those shifts, which is the IC extension of trivial local system orbits. And turns out this is the same as the corresponding block on the real side. And now, turns out there's a Langlands dual distribution of both in this. So here, turns out this is representation of certain dual groups. So this is usually called a real dual group or the real dual groups. Well, maybe it's a complex, so maybe that's called Nadler dual groups. He proved that this is a Tanaka category. Hence, by Tanakian formalism, there's the algebraic groups which denote by this, such that the category is equal to representation. And here, turns out there's also a Tanaka group corresponding to this category. It's a rep G check spherical. So this is usually called a Gascoigne-Nadler dual group. Because they prove that this, again, Tanakian, hence there's a Tanakian dual group for this. And as a corollary of this, turns out these two are just the same. Okay. Just from here to here is just tautology because they're all compatible with those, so you get this. It's the application. So turns out there's a very explicit complete description of this group in terms of the combinatorics of a real group. So this L real is computed by Nadler using the concrete geometry of the real F1 line. Very similar to the case of complex group. But on the other hand, this group, at the moment, there's no explicit description of this group. It's a Tanaka group, but for example, the vowel group or the root data for this guy is not known. And it's simply because the spherical geometry is much more complicated than the real one. But as a corollary, we see that these two groups are actually the same before we do any computations. But then because on the real side it's easier, in particular, the vowel group and the root data of the spherical dual groups is the same as those from the structure theory of X. In other words, many people like Konop and Yanis and Venkatesh, they give a combinatorial definition of what is the dual group of X, which in turn just the combinatorial structure of the symmetric variety. They work with a more general setting of spherical variety. And but they don't know whether this Tanakian one is equal to the one they define. But now because of this, and because of this on the real side, we can really compute everything. We can confirm that actually their group is the same as this Tanakian one. So this is, yes. Okay. Yeah, I assume case can. That turns out this is still true for any case, for any set. But the equivalence I have to modify a little bit, restrict to some component. No. Okay, so this is one application from real and symmetric. And another application is from the other side. So this side we use the fact that the real geometry, this Frank-Grassmannian, is very concrete. In particular, everything is finite dimensional. But to deal with this, basically everything is infinite dimensional. It's very complicated. For example, even in the original work to define this, to prove this, they have to use global models. So just so-called quasi-map, pick a curve, define using quasi-map to give a nice definition of this. So therefore, computing the root structure of this group is much more complicated. So now, the next example I want to talk about, so now I write symmetric. So we have the following result on the symmetric side. This is with the limit. So the IC complex of L plus G equivalent local system on L plus G orbits inside the X is pointwise pure. So we have this kind of pointwise purity result on the symmetric side. So you have a nice orbit, and you can consider, and with the local system, and you take IC. Turns out they said they're so-called pointwise purity. And as a consequence of this, we get so-called formality kind of result for so-called extension algebra. That's somehow the DG extensions algebra are formed zero convolve with it. Well, there's a very important object in the study of this relative Langlands or similarly in the theory of Coulomb branch. It's called this kind of DG extension algebra. This is the base point, the intersection cohomology for the closed orbits on your symmetric variety. And there's because of this work, there's an action, this dual group on this category. You can form this DG algebra. This is formal. So it's isomorphic to the extent that you take homology and the extension algebra with trivial differential. Then it turns out they are the same. And it's kind of well-known result that the purity will implies this due to Fingover, Roman Fingover. And this is on a symmetric side. And the proof actually it follows from the construction of certain transversal slides, constructions of conical, we call Mars Springer slides to L plus G orbit closure in So with Limfei, we construct certain conical transversal slices to OB closures with nice property. And then again, it's also known that if we can do this, then you have this. So this is on the symmetry side. We'll use the fact because here you have a very powerful tool in algebraic geometry, like serial weight or Hodge theory. But then you can translate this to a real side. You get the following a little surprising result. Namely, because on the real side, we don't have Hodge theory or serial weight. And so usually this kind of formality is not expected. But it turns out, or is that the so-called real, e.g. extension algebra, we can form similar things on the real Grassmannian or zero. Right. Do you think it is formal? So this is simply because it is real symmetrically compatible with all the structure. And this is kind of surprising because you don't have kind of this kind of general tool applied to this setting. But nonetheless, this is true. And so another corollary of this, so this result on the real side was used in the proof of the real and also relative Satake equivalence for the so-called splitting rank symmetric pair. So which are those the following? You can have x is like sp to n not to n, and also so to n minus 1 to n, and this exceptional f2 6. And these three symmetric pair plays an important role in the classification of symmetric variety. They are somehow in some sense, the simplest one. And the one reason is that, and we can basically use this formality result to give a full description of this whole category in those three cases. And the reason is that the corresponding real form or the corresponding real Grassmannian is very simple. In this case, it's just basically related to so-called quaternion projective plane in minus 1 h. This is a quaternion. And here, this is related to just a sphere. And here is related to so-called Arctonian projective. So this is the projective. And those things are kind of easy to handle. And then with this formality, we can do kind of various computation on the real side and prove real things, real Satake. And then by real symmetry, we can prove the relative Satake in this set. So those are the two applications I want to talk about. One is from the real to symmetric, where the real side of geometry is easier. And the second one is from symmetry to real, where on the symmetric side, you have more powerful tool in algebraic geometry, then you get some intrinsic result on the real side. And we expect this equivalent have more application, for example, understanding this kind of relative Satake or Coulomb branch associated to symmetric variety in general. I think this real and symmetric correspondence will be a useful tool. Okay, okay, I think I will start my talk here. Thank you for your attention.
Thank you for the nice talk. Any question from the audience?
So you take this convolution with the shift support on the base one. What category you get?
Yeah, those category, yeah, so say on the symmetric side, you can have this. Yeah, so this kind of perverse G. There's a Hecker actions. There's X on this by left convolutions. And the thing you talk about, it generates exactly this principal block I talked about. And this is known as rep G by definitions, separated. And the map is like a restriction. The thing you generate by Hecker action is this principal block.
Okay, thank you.
Yeah, a related remark is that turns out this thing is very, very interesting because it has a fusion product. This is a billion but not semi-simple, unlike the case of complex group. It has a fusion product which is monoidal and braided, but in general not symmetric. So it's very interesting to give a description of this because it won't be algebraic group, it will some kind of quantum group because it's not symmetric. For example, you talk about the case of disconnected K, like ON. This case were related to quantum group. But the thing they discuss is just only this part.
Any other question? So is there a derived version of relative Satake? Derived version of relative Satake. You don't just consider perverse sheaf, but rather than the derived category.
Yeah, so to give a whole description of the derived category is, so of course you can have the whole, this whole. And then turns out it's the same as what is the spectral description for the bundles on sheaf on bundles on real P1. So I don't have a full description, the exact answer for this. But under some assumption on the spherical variety, which is now people call hyperspherical, then this category appears in this work of relative Langlands by Yanis, Benzavi, and Sakharov, and Venkatesh. And then they propose the answer for this under certain assumption on X. And that should be, in that case, we do have an expected answer. But the gain is the same. So turns out from those general results, there's a description of this just as a cross correlation of certain vector space portioned out by some group. But the point is that can you give a combinatorial and explicit description of those space? Or in other words, in the terms of Coulomb branch, how to describe the Coulomb branch? They propose a recipe, combinatorial one, under some assumption. And now the job is to how to identify those two.
Okay, now let's send the speaker again. So we'll come back in 15 minutes.